Welcome to this presentation about transmission electron microscopy, most commonly abbreviated as TEM. We will first start by a brief introduction about electron microscopy and the basic working principle of a TEM. Then we will move on to its operating modes as well as their underlying principles. The instrument and its optics allowing for the practical implementations of these modes will then be discussed. Finally, we will showcase several examples and conclude on the advantages and limitations of the technique.
Why do we go to such great lengths to perform electron microscopy? The first gain over visible light microscopy is resolution. According to Rayleigh's criterion, the minimum distance we can detect between two elements is a function of the wavelength. Since the electron wavelength is a function of the electron energy, high-energy electrons allow us to reach really small wavelengths, such as 4 picometers for an electron accelerated at 100 keV. However, practical resolution is limited by the available electron lenses. Second, as we have already seen, the interaction of electrons with our sample generates various signals, and modern TEMs take advantage of many of them to provide information about the sample. Finally, using electron microscopy allows for electron diffraction, which is, as we will see later, a powerful method for periodic lattice characterization. More specifically, transmission electron microscopy consists in focusing a high-energy electron beam on a thin sample. Elastically scattered high-energy electrons are then transmitted and focused to form an image. The two main characteristics of this method are its exceptionally good resolution, which can go below the nanometer, and the required thickness of the sample, which is usually around or below 100 nanometers. Here, using Monte Carlo simulations of the trajectory of electrons in an indium gallium arsenide sample, we provide an illustration for why both high-energy electrons and a thin sample are required to make our material electron transparent, with the best results being obtained when both conditions are met. When compared to other characterization techniques, and most particularly to other imaging techniques, TEM's resolution is unmatched, making it particularly adapted to material characterization at the nanoscale. After this brief introduction, let us detail the operation of such a technique. TEM allows for two main operation modes, imaging and diffraction. The first reproduces the illuminated area as it can be observed in real space. On the other hand, diffraction corresponds to the reciprocal space representation of the sample. The optics allowing for the change between those two modes will be detailed in the instrumentation section. Let's start with diffraction. As seen during the course, the radius of the E1 sphere is inversely proportional to the wavelength. In the case of TEM, the wavelength is so small relative to the lattice spacing that the E-wall sphere can almost be seen as flat, allowing for a lot of diffraction sites to be included into the measurement. Rewriting Bragg's law, we obtain the following equation. Lowercase d, the lattice spacing, can be computed after measurement of uppercase d, which is the distance between two diffraction spots, since we already know L, the camera length, and the wavelength. Furthermore, when comparing electron diffraction with X-ray diffraction, the former is often more intense, due to its interaction with both electrons and the nuclei. Selected area diffraction, whose implementation will be discussed later, allows for the analysis of a really small area with an adequate intensity. Let's go back to the other operating mode, TEM imaging. A black and white image is made out of contrast. In TEM, several mechanisms contribute to this contrast, and we will review three of them. First, contrast can be generated by variations in mass and thickness of the sample. Heavier atoms and thicker areas will scatter the incoming electrons more, causing variations in intensity on the final image. On the central figure, you can see how thickness and mass information can be combined to provide 3D representation of latex particles. Moreover, reducing the aperture can lead to higher contrast, as more scattered electrons will be excluded from contributing to the image. In crystals, a similar mechanism can appear, but this time electrons are scattered due to diffraction by the periodical lattice. This mechanism, unlike mass thickness contrast, is very sensitive to the simple inclination angle, which can be modified to highlight material features. Another mechanism contributing to contrast in TEM images is the phase difference between directly transmitted and scattered beams. Due to the alternance between constructive and destructive interferences, fringe-looking intensity variations will appear, allowing us to retrieve information about the atomic structure of the sample, leading to high-resolution TEM. We will conclude this qualitative discussion on TEM imaging by talking about bright and dark field images. We have seen several physical mechanisms contributing to the contrast of our images. But we can also mechanically affect the transmitted beam in order to modify the final image. While the details will be discussed in the instrumentation section, we can already define bright field images as obtained by selecting only the direct beam, while dark field images are obtained by selecting diffracted beams. Hence, on the example below, dark field allows for excellent contrast by highlighting diffracting elements of the sample, while bright field images are the closest you can get to obtaining an actual picture of your sample.
In the following section of the presentation, the optics of the TEM instrument will be detailed, and several examples will be showcased.
From top to bottom, the TEM column is composed of 5 main blocks: the electron gun, the condenser lens system, the simple chamber, the objective lens system, and the projector lens system. The electrons emitted from the gun is sent to the simple by the condenser lenses, and the scattering beam is formed onto image by the objective lenses. The image is magnified and visualized by the system of intermediate and projector lenses. The electron gun, also called the emitter, can be divided into 2 categories: thermo-ionic emitter and field emission gun. The thermo-ionic emitter can be a bent filament of tungsten or sharp tip of lanthanum hexaboride. In this type of gun, a current is applied to the filaments to heat them up, and electrons are emitted from the tip. The field emission gun is composed of a polished sharp tip and an electric field placed below the tip to pull the electron out of the tip. All electrons coming from the gun, after passing through the first magnetic lens C1, are focused at a position called crossover. The electrons are better focused when they are coherent in space and time, or in other words, when they all have the same direction and speed. Field emission gun provide the most coherent electrons, but it's also much more expensive than the 2 other types of filament. The next block of the column is the condenser lens system. In general, the condenser lens system contains 2 lenses, C1 for the brightness of the incident beam and C2 to focus the beam onto the specimen. Below the C1 lens is the first condenser aperture, which select only a certain radiation and eliminate those far from the optical axis. Varying the strength of the magnetic field in C1 will move the crossover point up or down and thus change the number of electrons coming to C2. In a TEM, the illumination can be parallel or convergent to a single spot. Varying the strength of C2 will make the beam under focus, over focus, or focus, and hence change the area illuminated by the electron. If the TEM possesses only 2 condenser lenses, the parallel illumination is obtained by underfocusing C2 to obtain a quasi-parallel beam. Perfect parallel illumination is only possible if a third lens, C3, is inserted. The objective lens system is located under the simple chamber. After interacting with the specimen, the incident beam is scattered and the electrons coming out of the specimen can either be direct beam or diffracted beam. The objective lens collects the parallel beam exit the specimen and focuses them to form an image. The objective lens had 3 main components: the lens, the objective aperture located at the same level as the back focal plane, and the selected area aperture at the level of the image plane. This ray diagram explains what the back focal plane and the image plane are. Suppose that the specimen AB is in the object plane and the convex lens has the focal point F' here. The image A'B' of AB can be constructed by intersecting these 2 beams. The plane where A'B' located is called image plane. Suppose that the condenser lens sends parallel incident beam onto the sample. Some of them interact weakly with the specimen, and the beam exit the specimen are parallel to the optical axis. These beams are focused at F' and form the image A'B'. However, some of the incident beam interact with the specimen, and the imaging beam form a certain angle with the optical axis. These beams still end up at A' and B' in the image plane. It can be observed that these rays intersect at a point in the back focal plane. The back focal plane is where the focal points of different parallel beam families located. In TEM, the position of the sample at which the image is optimal is called the eucentric position. There are two ways to find the eucentric position. The first way is to keep the position of the sample and change the current in the objective lens until it's well focused. And the other way is to keep the current in the objective lens and change the position of the sample. Varying the strength of the lens is preferred when a lot of tilting are required, and varying the position of the sample is preferred in high-resolution TEM. A TEM can give two types of information, the image and the diffraction pattern of the sample. If we want to look at the diffraction pattern of the sample, the intermediate lens must take the back focal plane as the object plane. If we want to look at the image of the sample, the image plane must be taken as the object plane. And how to choose what plane to take as the object plane? We simply need to vary the current in the intermediate lens to change its focal length. To switch from imaging mode to diffraction mode, one needs to weaken the strength of the intermediate lens so it will look further up and reach the back focal plane. What makes TEM become a powerful technique is the alternative use of two apertures, objective aperture at the back focal plane and selected area aperture at the image plane. The selected area aperture allows to choose a specific area where we want to look at. For example, a grain on an image and get the diffraction information of this grain. So why don't we just focus the beam to illuminate just this grain, like in SEM? It's because if the incident beam is converged to a spot, it's not parallel anymore. So the better way to look at that specific grain is to illuminate the whole sample, but to choose only the beam from this grain to look at. The objective aperture permits to select only a certain diffraction plane to look at. A more precise example will be given later to clarify the use of the two apertures. When using the objective aperture, one can work in bright field or dark field mode. In bright field mode, the objective aperture is placed on the optical axis at the back focal plane, so only direct beam is chosen to image. In dark field mode, the diffracted beam is chosen to image. Dark field imaging can be obtained by two methods. The first one is called dirty dark field because the objective aperture is off-axis, so spherical aberrations can make the image blurred. The correct way to do dark field imaging is to tilt the incident beam so that the diffracted beam is parallel to the optical axis. To clarify all of these, let's move on to a precise example. The sample is a barium titanate powder which is prepared by grinding to break down the agglomerate. The first image we see here is the TEM image of the grain. When the selective area aperture is inserted, only the area inside the circle is chosen, so we exclude the particle up here. The diffraction pattern shown here is that of the selected area and not of the whole image. Next, we'll look at the diffraction pattern of the image in bright field mode. The objective aperture is put around the transmission spot, which means we only select the direct beam and eliminate the diffracted beam. We can see that the image on the right is much clearer than that on the left, is because by eliminating the diffracted beam, we minimize the recombination of the intensity of transmitted and diffracted beams. Finally, we look at the diffraction pattern in dark field mode. Using the objective aperture, we select a first diffraction spot with weak intensity. We then go back to the image mode to see from which grain or which part of the grain comes the chosen diffraction. The intensity of the chosen spot is weak, so the brightness of the whole image is increased. This part of the grain is slightly brighter than other parts. It can be concluded that the chosen diffraction is from that part of the grain. The second diffraction spot chosen is brighter than the first one, thus we see better contrast. The bright part in the image corresponds to the elements of the sample that are diffracted.
We can conclude this presentation by reviewing the strengths and limitations of TEM. Its obvious advantages are the unmatched resolution, the optics allowing for small area analysis, the variety of complementary signals involved, and its large availability and flexibility. However, time-intensive sample preparation is required, and high resolution comes at a financial cost. Vacuum is, as usual with electron-based techniques, mandatory, and the sample might be damaged by high-energy electrons. Finally, a word of caution. While TEM images might be impressive, they must be handled cautiously, while keeping physical context and principles in mind.